So let's start. Rosatom. My presentation basically is quickly three parts. The one is overview of Rosatom, who we are and what we do. I understand my pre-speakers here are much better known here in the Netherlands, Rolls-Royce and especially EDF. So as Rosatom, yes, everybody has heard our name, but I'm not sure you all really know what we're doing. Second one, some highlights of our main product these days. And I'll get back to that at the end. And the third one, insights in our current international projects. We as Rosatom are the largest fully integrated company in the nuclear sector globally. We have more than 250,000 employees and at the same time are spending almost 5% of our revenue in research and development and in continuous improvement. At Rosatom, we are including everything that is nuclear. It basically starts from mining, it goes through enrichment, design, manufacturing, operation, all the way to unfortunate topics like decommissioning. Yes, we have to do this too. Comparing us with European entities, yes, you could say a combination of EDF, Framatome, Orano, and the CEA still doesn't cover the breadth of everything that Rosatom is doing. At the same time, we are also branching out, as you see on the right side of the slide, into related areas. We are operating the nuclear icebreaker fleet of the Russian Federation. We are doing nuclear medicine. We are producing isotopes. And we are now relatively strong also in new materials. In today's world, and considering also the context of the United Nations Sustainable Development Goals, we are really proud to contribute into the carbon dioxide reduction worldwide that will enable to reach many of those goals. The electricity produced by our reactors today avoids or is as efficient in avoiding carbon dioxide than three times every tree in Germany. So going with the speakers before me, we believe nuclear is one part of the solution. As a supplier, partner, or customer, and we are playing all roles globally, we have proven over a long time that we are really reliable. This reliability is reflected also in our financial performance and in our financial ratings, without going into the numbers, but you'll have them. We are global. Most of our market companions are. So we are everywhere, and for obvious reasons, you don't see any permanent representations in North America. But believe me, we have a multitude of projects working together with US and Canadian companies. As a utility behind EDF, we are the second largest operator of nuclear power plants. So our fleet of 37 nuclear reactors, and you see one of them is this FPU, this floating power unit. Academic Lomonosov, you'll see a picture of that. It's a small one, so we are having even a floating small modular reactor already operating, but that was a joke. We are producing 20% of all the Russian electricity, and if you look at the technology we are using in the right lower corner, most of that is done by our VVER technology, which I will give you a few details later in the presentation. I already mentioned that we're spending a significant amount of money in research and development. So only a few examples here. We just commissioned, I think last year, the world's only so far floating nuclear power plant. The second one is going through commissioning trials and will become available by the beginning of next year. And we are the only operator at the moment who has fast neutron reactors operating reliably already for decades, and our BN600 is also being exported outside of Russia, and we are currently constructing a larger unit. This will allow us to finally close the fuel cycle starting in Russia, which is one of the mid and long-term goals of Russian nuclear. At the same time, we're working here in those reactors on industrial scale transmutation, again to eliminate, within a few decades, I gotta have to admit, the problem of long-term disposal of radioactive waste. Yes, we're doing SMRs. Floating nuclear power plant is an SMR. We're also building different other designs of SMRs and Gen 4 reactors, but this is not what I want to speak about today. Just to have that slide, we can do this too. If somebody's interested, I'll be more than happy to provide more details. We are not only supporting research in our own organization, but we have built the largest number of research reactors in the world. Now going a little bit into the more details what we are doing. Nuclear power today relies almost exclusively on uranium. That may change in the future. Thorium reactors are being discussed for decades. Maybe one day they become the mainstream. Today it is uranium, and for the foreseeable future it will remain uranium. We own around half of the world's known reserves, and most of the uranium we are mining is actually used not inside Russia, but is powering reactors outside of Russia. Uranium conversion and enrichment. I hope everybody of you knows that the centrifuge is a Russian invention. When everybody else was still working on gas diffusion plants, wasting incredible amount of energy, in Russia the centrifuge was invented and developed for the enrichment. So we have been a major part here, and still today are the largest, by separating work units, we are the largest enrichment company in the world. And again here, our enrichment services are used mostly by operators outside of Russia. Logically, we produce our own fuel. We are producing fuel for our VVERs, for our other type of reactors. Globally, we are producing fuel for many of the research reactors, very specialized fuel, as you know. And we now also have a fuel design that we call Quadrat, for obvious reasons, that would fit into Western PWRs. And the first successful trials have been completed recently, so you may see us also offering fuel to Borsod at some point. No, this fuel we are not looking into. I'm sorry, this design is too old. All the equipment for our nuclear power plants, all the manufacturing is done in-house. So this way we can ensure that we have constant, adequate, equal quality of the products, that we have full control of the supply chain, because it is ourselves, of those critical components, and we continuously improve not only the component design, but also the manufacturing methodologies. You see our current capacity is to produce up to 4 complete primary circuits per year. Given our own fleet and the huge amount of maintenance experience that we have at our fingertips, we have now also successfully started to offer maintenance services outside of Russia. And this is growing constantly to support operating units, but also as an integral part of our new projects and our new delivery models. But a few words about that you will also hear later. As stated at the beginning, we're covering the entire scope. So all aspects of spent fuel management are part of our core competency, from storage to reprocessing. Our recycled uranium has also been used in Borssele to fabrication of mixed oxide fuel elements. Again, all of that done entirely in-house. And I don't like to talk about it, but it is part of our business. After 60 to 100 years, we also have significant competencies in decommissioning and final disposal. So, in 1954, in Russia, the predecessor of today's Rosatom connected the first time ever a nuclear power plant to the grid. That was years before the same thing happened with Shippingport in the United States, or even a couple of years later with Calderwell in the UK. So you see, our history goes back a very, very long time, and since then we've been doing nuclear, and nuclear. Until today, with more than 100 units designed and successfully constructed all over the world, mostly of them are outside of Russia today. Now we are coming to the second part and the more technical part, after I hope I gave you an overview on what Rosatom is and what our capabilities are. Unlike others, we never stopped improving, designing, and constructing. 17 large-scale reactors commissioned over the last 15 years, I think, speak for themselves. And I'll get back to that. Just take my word for now. We know that based off hundreds of years of reactor operating experience and our continuous improvement, the VVER-1200 that I'm going to give you details here is the safest and one of the most reliable nuclear power plant designs on the planet today. And some of its key features I'm happy to present you. Yeah, on this slide, you just see the key parameters. Nothing too exciting about it. So ultimately, it's just a pressurized water reactor. Yeah, 3,200 megawatt thermal. As the name VVER-1200 already indicates, 1,200 megawatt electrical availability and so on. You would see that from other PWR designs. So absolutely competitive. I can call it state of the art. So I don't think anybody has anything significantly better to offer at this point in time. Let's go a little bit more into details. I hate this. I'm sorry, I'm not one of those fancy, I like slides that I open and then I see them. So our VVER-1200 is a 4-loop pressurized water reactor, very much comparable. If you look here at the picture of the primary circuit, you can easily recognize also a Westinghouse 4-loop, a Siemens Convoy, whatever. The concept is very similar. Where do you see here the main differences? Now, let's start with our steam generators are horizontal. And I'll explain you later why they are horizontal and why they will always remain horizontal. Vertical steam generators are just a design flaw. So second one you see is our reactor pressure vessel is much slimmer. I have to admit that that is not something that we designed as such, but it was dictated in the past by having the requirement to be able to be transported by railway. So the diameter was limited by the railway tunnels in the past, but that led to the fact that our inlet and outlet nozzles of the primary circuit are not at the same level but the outlet nozzle is on the upper side, the inlet nozzle is on the lower side. Just the natural thing that you would expect for gravitational flow that allows a much simplified design of the core internals and ultimately also improves the safety and the thermohydraulics of the core. And the third main thing is our pressurizer is substantially larger than in comparable designs. So one of our design philosophies, more about that later. The history of our current, and I'm not going back all the way to VVER. The VVER started somewhere in the 60s as a 100 megawatt prototype unit, then went on to the VVER 440 units with quite a few operating. I'm sure you're aware of Loviisa and Paksh and similar units. There's quite a few operating in the European Union. But in the 90s, there was a big push for innovation. And one of the major things here is what you see, the VVER 640. The VVER 640 was never built. The VVER 640 was a cooperation between Rosatom and Siemens Nuclear. So we basically took the primary system, the mechanical system, the process systems that we had developed on the Russian side, and we married them with the safety philosophy of the Convoy Plus, which by the way also was never built, and jointly with colleagues from Siemens at the time, developed and qualified all the passive safety systems. From there on, the design evolved in multiple steps, and coming to today's VVER-1200 that I'm talking here about, we have currently 3 units operating, 2 in Russia, Leningrad phase 2 units 1 and 2, and the first unit in Belarus is operational since mid of this year. The second one is just finalizing the hot trials, and I'll show you the examples. We have quite a few of those units under construction at the moment. Back to technical things. The one underlying VVER philosophy, and I've touched that on the pressurizer earlier, is we have as much water inside containment everywhere as possible. The more water you have, the better. So our primary circuit in cubic meters of water per megawatt thermal is much higher than any other design. Our secondary circuit, details later, has much more water than anybody else. Our pressurizer is bigger than any other design, and all our emergency water tanks are inside containment. So we have a considerable inventories of water, which just increases substantially the forgiveness of the process systems to any kind of unexpected transients and increases operator response times substantially. A friend of mine who used to be a shift manager at a VVER 440 always said, you know, Alexander, our problem never was to get them operating. Our problem always was to keep them going. Every little mistake we would make, they shut down by themselves. Okay, for the larger units, that's probably not as true anymore, but the underlying design principle is still the same. If I look at other designs, many of them always say, are so proud that they have passive safety systems. Great. And by passive safety systems, you can replace all those expensive, hard to build active safety systems. And you can build much cheaper and much faster. By the way, if I'm looking at projects like VC Summers or Vogel, this cheaper and faster hasn't materialized yet. So on paper it looks great, but we haven't seen it yet. For us, this is just plain and simply not an option. A passive safety system provides diversity and redundancy and not replacement. Full stop. So let's start with a few simple things, okay? We have a double wall concrete containment, the inner containment fully pre-stressed, lined with an 8mm steel liner, fully welded on the inside, annulus under reduced pressure with filtering to the outside. Every reactor should have that today. Some don't, but we believe every reactor should have that, and many of them do. Then let's get a little bit more sophisticated. A corium localization device, commonly talked about as core catcher. I'm just going to use core catcher here in the future. This thing gained a lot of attention, especially after what happened to those units in Fukushima in March 2011, I believe it was. We commissioned the first one in 2006. So long before the world started really looking seriously at that issue, in a VVR, this thing was already operating. Core catcher obviously protects the containment floor in the event of the hypothetical event that shall never happen, so that the corium will stay inside containment, but the core catcher does a lot more things. Here you see core catcher is an integral part of increasing the safety of the plant. It avoids all the X-core hydrogen generation mostly. So hydrogen explosions will not happen. It avoids the molten core concrete reaction, which is responsible for most of the X-core generating hydrogen and carbon monoxide. And it ensures long-term subcriticality by melting into the core adequate amounts of neutron absorbers. Oh, I said 2006, now I'm not sure, it may have been 2007 or this may be a typo, but as mentioned before, the core catcher, the first core catcher ever going operational Tian 1, Unit 1 in, let's stick with 2007. Concept of passive cooling through pressurized accumulators. I see that in many presentations of others, so I thought I'd put it here too. I think this is same old Borssele has that. Every PWR on this planet, generation 2, has high pressurized water containers to inject into the primary circuit in case of loss of coolant accidents. So nothing really great on that. This passive system has been there all the time. Look at the details. Does everybody have 2 stages of independent passive accumulator systems? Most passive accumulator systems and other designs inject into the primary loop with all the known problems there, if you look at it. Ours inject always directly into the pressure vessel. Then the feature we really are unique in. No other design I'm aware of. No, this is not entirely true. If you're now looking at the new Chinese Hualong, they have learned from us, and they will have that too, but they don't have one of them operational so far. So operating, we are the only ones where the design exhibits self-actuating passive cooling systems which transfer, in case of a beyond design accident, energy directly to the outside of the containment into the atmosphere outside. Let's look at the 2 main systems here. The one is the containment passive heat removal system to avoid overpressurization of containment and secure the containment after the hypothetical, again, severe accident. You have plate condensers all around the containment dome, which are directly connected to a large water tank outside the reactor building, on top of the dome. There is no isolation valves in there. Once the containment should heat up, natural recirculation will automatically start and transfer the energy from inside the containment to those water tanks outside. It says 4 times 33% here. I'm not going to talk about it because this is really extremely dependent on the accident scenario you're calculating at the time of the accident you're looking at. So this is kind of an arbitrary number, but under all circumstances, 72 hours of complete independent operation are the absolute minimum for this system. A steam generator passive heat removal system using the same tanks outside, but the piping now being directly connected to the secondary side of the steam generator. In case of a complete loss of power and even the inability to do feed and bleed through the main steam valves, this passive system will keep the primary loop cooled for days and days and days and days. Actually, one of the limiting factors here is the main coolant pump seal leakage at the end of the day and not the heat removal. Let's get a little bit more conventional. Yes, we design, qualify, and manufacture passive hydrogen recombiners, so do others. We have qualified codes to do the hydrogen distribution inside containment and determine the location of, or the placement of those recombiners, so do others. Yes, we have it. And every PWR should have it. Interesting, US PWRs don't have it. There was an NRC decision saying that for PWRs, hydrogen is not a risk. So I presented them years ago. Then hydrogen, our system, and then I had the American PWR, and every hydrogen molecule had a little American flag on top of it. So American hydrogen is not a risk, but everywhere else in the world it is considered a risk. Okay. Nevertheless, going back to the philosophy I mentioned earlier, all those systems protect the containment under beyond design base accidents. We still have the active system. We would never even think about giving it up. Yes, we're having an active containment spray system to reduce the pressure inside containment after an accident. Yes, it is there. And it is being even constantly improved. We're adding chemicals to basically ensure that all the radioactive iodine remains down in the sump, and that the iodine, even in case of small containment failures, does not get to the outside and is jeopardizing any people. Summary here says it all. Diverse and redundant systems. There is no or. Diverse and redundant systems. And all the systems I've shown you here have answered all Fukushima-related questions a long time before the event. Reactor pressure vessel. New materials, qualified for high neutron flux, easily goes for 60 years. Improved thermohydraulics due to the staggering of the nozzles, I talked about it. Minimized welds, no vertical welds at all, no bottom penetrations. Now my favorite topic. Horizontal steam generators, frequency of replacement 10 times less than on vertical steam generators. That says it all. But no, I started with nuclear services. I loved steam generators. There is no other component for a service company to make more money with. The amount of inspection, amount of repair, amount of maintenance and other services on a steam generator is incredible. We were making money, money, money. If I'd still be in nuclear services, I'd really hate those horizontal steam generators. They don't need all of that. And beside the many design features that make it easier to operate and maintain, they even make the plant much safer. Details during lunch. We also design and manufacture our own main coolant pumps. They are fully water-cooled, hydraulic and electrical. No oil fires. Forget about that risk. Doesn't exist. Our fuel is hexagonal, and this is a good thing. The hexagonal is the densest possible packing of spheres. This is just a simple fact. How somebody can even think about making square fuel, I don't know, but many people do. So we get easily 7% more uranium in the active core. The hexagonal geometry physically is much, much better for coolant flow. Don't need fancy calculations, it's very easy to demonstrate that. And in the case of whatever accident during storage or transport, hexagonal fuel will never stack itself densely. It's impossible. So there will never be any criticality concerns under those considerations. Yes, we have superior reactivity control. We have more control rods than anybody else. We don't need boron. Even at low temperatures, we don't need it. But again, we have it. So turbines, we are not manufacturing turbines. The VVER-1200 at the moment is operating with a Russian turbine from Power Machines running at full speed, or alternatively with a GE steam power systems, formerly known as Alstom, at 1500 RPM. So whatever is the customer wants, we do. Let's quickly flip through a few projects. Hanhikivi, this is important. Hanhikivi, 1200 megawatt unit in Finland, construction license expected sometime during next year. But why is it important? We believe in nuclear and we believe in our product. We have skin in the game, as the Americans say. So we own the customer to 34%. We are financing with our own equity into our own project, and we will stay with this project until decommissioning. At the same time, somebody talked about, Olivier, I think, about public-private partnership. Here we have a public-private partnership, not with the Finnish government. The Russian pension fund is financing part of this project. So as country, we believe into nuclear, and even our pension fund is investing in nuclear outside of Russia. Paksh, 2 units, construction license expected in a few months, 2 VVER-1200, river cooling, not seawater cooling. Another project in the European Union, Rosatom. Framatome. I'm not Framatome anymore, sorry. I used to be there 20 years, now I'm Rosatom. 80% of the financing arranged with the help of Rosatom. Akuyu nuclear power plant, 4 VVER-1200 units in Turkey. First one started, got construction license in 2018 and will go operational before 2025. The other 3 units staggered one after the other. I can happily announce that 40 minutes ago it went through the press that we got construction license for the 4th unit, so concrete will flow already this year. 100% owned by Rosatom. Nobody else is doing this. We believe in it. We build, own, operate. We put our own money on the table. Belarusian nuclear power plant, 2 units, the first 2 in the plant. Aldaba, 4 VVER-1200 units, construction license imminent. All the preparatory site work is ongoing. We're talking with the Egyptians about a second site on the other side of Cairo, another 4 units. Koninklijk, one of our success stories, the first units operating since, I must say here somewhere, it doesn't matter. No, yeah, operating predecessor units, VVER-1000 units, having double containment, core catcher, and the first plant ever having that full-sized passive heat removal systems. And they have been tested there. We have the real life test of all those passive systems since Koninklijk. The customer liked us so much that he ordered another 4 units. We are currently having 6 units there, 2 operating, 4 in different stages of construction. Ropur, 2 VVER-1200 units, first units in Bangladesh and the country. We are also developing the whole infrastructure around it for the country. Tianwan, I already mentioned, the first core catcher in operation. Cooperation with our customers there went so well that at the end on this side there will be 6 VVER units, 4 of them already operating. The other 2 got construction license in May this year, so are under construction. And we already have submitted the preliminary safety analysis report for the second site with, at the beginning, 2 VVER-1200s in Jodhpur. So thank you very much for spending a few extra minutes of your lunch with me. I hope I gave you a good overview of what we are and what we have to offer. Again, if there's any questions, anytime. Talk to me here, send me an email, we will respond.
Thank you, Walter.
Okay,